I'm Yokota from the Tokyo Institute of Technology, and today I'll be talking about how to pre-train vision transformers with synthetic images. Okay, so the reason why we are looking at vision transformers is because there is such a thing as a scaling law. And am I allowed to take my mask off? Okay, so as you know, the size of deep learning models is increasing exponentially, and the exponential rate is much larger than doubling every year. It's actually, I think, an order of magnitude every year at this point. Of course, this is not sustainable, but until now, models like GPT-3 were considered large, but that's not the case anymore. The largest one here was done on, the Chinese supercomputer that is predicted to be exascale. That is, not really existing on the top 500, but the models that you can train on these largest machines is around this scale. So that this sort of gives you an idea that we can actually, with HPC capabilities, we can compete or outcompete with people who are training GPT-3, for example. And so I wonder if there's a way to delete this thing here. Oh, okay. All right, well, I guess it's fine now. So it's impossible to train such large models without supercomputers. And it's not just the size that's, oh, why is it playing a slideshow? Okay, so as you know, these vision models and language models have evolved in terms of their architecture. And nowadays, transformer seems to be the model of choice, not just for natural language processing, but also for vision tasks, because there is such a thing as a vision transformer, where you feed in patches of images that, in the same way that you feed in words, and these models scale when you increase the model size and the size of the data set that you train on. And you can see this in the original vision transformer paper. This figure is taken from that paper. And what this is showing is that if you only increase the model size from like this pink one to the blue one, but you still train on the small ImageNet data set, then you don't really get a performance increase. Also, if you just increase the data set size from ImageNet 21K to JFT, but you don't increase the model size, then you don't really get this accuracy boost. And so what this means is we need really large models, but at the same time, we really need large data sets. And the reason why we are not getting good scaling laws for vision tasks yet is probably because we don't have large enough vision data sets. And so the critical thing is to have these huge data sets. However, as some of you may know, JFD300M and JFD3B are only accessible to Google. So basically the rest of the community is stuck. Even if we had supercomputers like Frontier, we don't have the data to train them on. And so this is a very critical problem. Even with compute, we don't have the data. And so that's why, well, so in the beginning, we were looking at different options, like why don't we crawl the web ourselves? But eventually, we started collaborating with some people who were looking at synthetic images. And what they do is they use these functions to generate these kind of fractal images. And with this, you can generate, any quantity of these various image types. And so if you train a vision transformer based on real images, you get this purple line here. And if you train on these synthetic data sets, it gets very close. And the gray one is without any pre-training. So how you train these vision transformers is you first pre-train on a humongous data set, and then you fine-tune with small amount of data for your specific task. And if your pre-training data set is large enough, it will pre-train the vision transformer in a way that generalizes to multiple downstream tasks. And so if you use this data set, this synthetic data set for the upstream, the pre-training of your vision transformer, it gives you very similar downstream accuracy. And so we take this approach, which was done on ImageNet, so this is like 1 million images, and we want to scale this to 3,000 times larger, basically. And to get there, there's still a long way to go, and I'll give you some challenges that we faced. So the way data sets are stored, typically, for example, ImageNet, stores these PNG files per folder for each class. So each class is a folder, and you have, for ImageNet, 1,000 folders because there are 1,000 classes. And inside each folder, you have about 1,000 images each, which means you have about 1 million images for ImageNet. But if you store your data in this way, there are a few problems. First of all, if you take this and scale it to JFT scale, you're going to exhaust the inodes on your file system. And it's going to put a huge strain when you actually read the data. For example, when we tried to read 50 million images, and by the way, this was on the ABCI machine at AIST, the training didn't even start. It didn't even start the first iteration because it was loading all this data, and it was taking, something went wrong with the huge load of I/O suddenly being accessed by all the nodes. When we were using like thousands of GPUs, each GPU was accessing all this data. And so more recently, what people do nowadays is they use this thing called web datasets. There are other variants, not just web dataset, but you put all your images along with a file that indicates which class it belongs to, and then you pack this into a tar file, typically with like 10,000 of these image and class pairs. And then you put each tar file on each node, and then you just read your local file. So you can actually cache this on your local SSD if your system has such a thing. And so this is now quite standard, and this, first of all, puts a huge, releases the pressure on the inodes, and also it improves the I/O time drastically. Okay, and with that, now we can ingest a huge amount of synthetic images. So we tested with different types of synthetic images. We tested for different parameter ranges. We've also tested for, these kind of images with many vertices, like graphs, and changed the number of vertices. Also changed the number of points used to render the image. And we sort of tried to find the optimal hyperparameters for generating the data set. So it's a different kind of hyperparameter tuning. The good thing about this hyperparameter tuning is that once you're finished, you have a data set that performs well. Unlike normal hyperparameters where it doesn't really translate to other modes of training, this one just creates a good data set. And so there are various configurations for training these vision transformers. The typical one, the original vision transformer used this kind of configuration, whereas more recent efforts have improved the accuracy simply by changing the range of this configuration, changing the hyperparameters so that it performs better. One big difference between the original one and this date is that it trains for very different number of epochs. So the original one trained for only 8 epochs for the fine-tuning, but the date configuration trains for 3,000 epochs. And if you apply synthetic data sets for your pre-training, you need this configuration that trains for longer number of epochs, simply because ImageNet 21K is very similar to ImageNet 1K. So if you're fine-tuning on ImageNet 1K, then pre-training on ImageNet 21K transfers very well in a few epochs, because the domain is very similar. However, these synthetic images come from a very different distribution of data, and so we do need to train for a longer number of epochs. And then, so we did some experiments with different data set sizes, because we can increase this arbitrarily. We took this to like 100K classes, each with 1,000 images. And then for fine-tuning data sets, we used a variety of downstream tasks. These are all classification tasks, but more recently we've been looking at different tasks for fine-tuning, like detection and segmentation. But in this case, what I'm presenting today is only for classification. The models we used are of this size. It's not that large compared to what the language models are doing. But in vision, because your images are much larger than words, you typically tend to be very heavy on the activation instead of the parameters. So your activation are consuming much more memory than your parameters. And so for that reason, it also takes a larger amount of compute per number of parameters. And so it's like slightly different problem. Okay, so there's a bunch of numbers shown in this slide, but the one that is most significant is shown here. So only the top row is a real data set. This is ImageNet 21K, and the rest of the other rows, these are all different types of synthetic data sets. And as you can see here, as we increase the model size, the accuracy generally increases for everything. But compared to the real data set, we are getting very competitive performance and sometimes even exceeding the performance of ImageNet 21K pre-training. And we're still in the stage of scaling this up to get to JFT scale. We haven't quite gotten there, but we've increased the data set size to 50K classes and 100K classes. And the final accuracy that we reached is, I think the highest one is 83.7, which is getting pretty close to 84.2 from JFT. So we are getting very closer. And the good thing about our data set is that it evolves, right? JFT and ImageNet, they're static data sets that can't be changed. However, in our case, we can just keep improving, and it's only a matter of time until our data set becomes better, because it can be improved. Okay, so because we are a little bit behind schedule, I will make this my final slide. So I was talking about training on 100K classes, right? But is this really the right way to go, is the question. Because if you're classifying 100K classes, you have, like a billion images, and you're trying to bin them into a huge number of bins. And in the end, you get this probability distribution that's like mostly zero for all the classes. It's really not what we want to do. And also, it's very difficult to label things into like 100K classes, right? The labeling effort to do that is huge. And so I think there's been a transition in the vision community and also the language community, which is gradually merging, is that instead of putting like one word onto each image, which is the label, you want to put multiple words, maybe multiple classes, and then the final form of that would be to actually have a text that describes what's in the image. That's like a whole sentence, right? And so that's what's actually happening here with things like CLIP. You have image and text pairs, which are probably much easier to mine from the web. And there are huge open data sets now that are available for training with image and text pairs instead of a classification problem. And so I think this is the way to go when you want to deal with this huge amount of text and images. And also, we want to understand why this works. We haven't quite figured it out. We know empirically that we get very good results. But the reason why this is so is, well, always in this field, the theory lags behind. And so there needs to be some systematic investigation of what is actually happening that allows us to train on such synthetic images. Okay, good, because I'm done, so it's okay that, yeah, it's showing a black screen, but thank you. That's all for my presentation.